Hello students, this is Dr. Shivam Mishra and today I am here with the topic numerical problems on vapor compression refrigeration system. In my previous lectures we had already discussed about vapor compression refrigeration system, multi-stage vapor compression refrigeration system as well as the multi-evaporator refrigeration systems. So today we are going to solve numerical problems on vapor compression refrigeration system. So here it is the numerical. A vapor compression refrigeration machine with Freon 12 as refrigerant has a capacity of 12 tons of refrigeration operating between minus 28 degrees centigrade and 26 degrees centigrade. So here it is the condition. A vapor compression machine is working with a refrigerant Freon 12 and capacity of the machine is 12 ton and the temperature limits are minus 28 degrees centigrade and 26 degrees centigrade respectively. The refrigerant is subcooled by 4 degrees centigrade after the condensation before entering the expansion wall, and the vapor is superheated by 5 degrees centigrade before leaving the evaporator. So this superheating is after the before leaving the evaporator or before entering the compressor. The machine has a 6-cylinder single acting compressor. So number of cylinders is equal to 6. With the stroke length equal to the 1.25 times the bore. So L by D, the ratio of L by D is equal to 1.25. It has a clearance of 3% of the stroke volume. We will discuss about this. So what we have to determine are, the points are the theoretical power required. Second one is the COP of the system. Third one is the volumetric efficiency, and fourth one is the bore and the stroke of the cylinder. Also we have some data given that speed of the compressor is 1000 rpm and the following properties of the Freon 12 may be used which are given below. So what I have to say is, before solving these numerical problems you must have the basic information about the enthalpy calculation as well as the entropy calculation within the vapor dome or outside the vapor dome, that is subcooled region or the superheated region. Also you must have the refrigeration table before starting to solve these numerical problems. So the properties of the Freon 12 are given here. You can also read it by the refrigeration table. And the specific heat of the liquid refrigerant is given as 0.963 kilojoule per kg Kelvin. This is for the liquid refrigerant. And the specific heat of the saturated vapor refrigerant, which is at the exit of the evaporator or within the obviously this is at the exit of the evaporator, is 0.615 kilojoule per kg Kelvin. So firstly I will discuss, before solving this numerical, firstly I will discuss about the basics, that how we should proceed while solving these numerical problems. I have represented this on a TS curve. You can also show it on pH curve as well, no issue. So this is your TS curve, temperature entropy curve. This is your cycle. The cycle may be at the evaporator at the exit of the refrigerant at the exit of the evaporator may be at the saturated phase, or it may be within the wet region as well. We will divide these regions at, this is known as wet region, this one is your superheated region, and this one is known as subcooled region. So refrigerant at the exit of the evaporator, let us assume it is in a saturated vapor phase. So this is your point 1, which is the entry point to the compressor. It goes to compressor if it is a single acting cylinder or a single acting compressor or a multi-stage compression. It goes to point 2, then it comes here at 2 dash, again at the saturation curve. This whole portion is of the condenser portion where the heat rejection takes place. 2 dash to 3 is your condensation where the heat rejection is taking place. Now again 3 to 3 dash, this is known as your subcooled region. This region is your subcooled region where the temperature of the saturated liquid drops again. So this is your degree of subcooling. This one 2 to 2 dash is known as degree of superheating. Again your refrigerant may be at point 1 dash, 2 dash, 3 and 4. It may be possible that your refrigerant has 1, 2, 3, 3 dash, 4 dash. Here we can see when we are doing subcooling, we can see that refrigeration effect is being increased in comparison to this one when there is no subcooling is there. Okay, so while solving the numerical problems, we must have data, we must have the equations to solve this numerical. Here we can see if in a wet region I want to find out the enthalpy, I have the formula H is equal to HF plus X HFG, where X denotes your dryness fraction and HFG is the difference of enthalpy at the saturated vapor phase to the enthalpy at the saturated liquid phase. So this is also known as your latent phase, that is the heat required for the phase change. Similar is for the entropy calculation as well, that entropy at any point within the wet region, within this vapor dome, is given, may be calculated as S is equal to SF plus X SFG. Similar is the case for the volume as well, VF plus X VFG, where HF is the enthalpy of the saturated liquid, as I already discussed, and enthalpy at the dry saturated vapor Hg. For the superheated region, we have again a different formula, that after the evaporator we can calculate this enthalpy at the saturated region as H is equal to Hg, that is the enthalpy of the saturated vapor, plus Cp T superheated minus T saturated, that is the difference of the superheated vapor, temperature of the superheated vapor minus the temperature of the saturated vapor. We also call it as degree of superheat. Similar is the case for entropy as well. We have a different formula, S is equal to given as Sg plus Cp ln T superheated divided by T saturated. And in some cases you will also find that as the formula goes to Sg plus 2.3 Cp log, this is your natural log, that is log base 10 T superheated divided by T saturated. So do not worry about the formula, both are the equal formulas, both are the same formulas. For the subcooled region, we have calculation as in we can find out the enthalpy as HF, that the enthalpy of the saturated liquid at, let us assume, at 0.3. So if I want to find out the enthalpy at 0.3 dash, so I will do like as H is equal to HF minus Cp T saturated minus T subcooled, that is the degree of subcooled region or degree of subcooling. So now we can proceed with this basics, we can proceed to solve the problem. So first of all, note down what are the given data for you while solving the problem. Capacity of the cycle was given as 12 ton of refrigeration, that is 12 into 3.5, that is 3.5 is the kilojoule per second, so we can find it out as 42 kilojoule per second. The temperature at point 1 dash, that is temperature of the saturated vapor at the exit to the evaporator, is given as minus 28 degrees centigrade, that is the lower temperature. Minus 28 degrees centigrade, we can convert it into the Kelvin. We have this form, now we can have this value 245 Kelvin. We also know that when we go from the temperature of 2 dash is equal to the temperature of 3 dash, because these are the same temperature line. It is given as 26 degrees centigrade, that is the condenser temperature line. It can be written as 299 Kelvin. Degree of cooling is given as 4 degrees centigrade, that is the temperature difference of T3 dash minus T3, you can see in this curve. Or T3 can be written as 22 degrees centigrade, because if you will subtract 4 degrees centigrade from this one, 26 minus 4, you can reach this value. So the temperature at T3 is equal to 295 Kelvin. Degree of superheating before leaving the evaporator is given as 5 degrees centigrade. Similarly, you can find out the value of T1. You know the value of T1 dash, now you can calculate the value of T1. L by D ratio is given as 1.25, and the ratio compression, the clearance ratio is given as 3%, that is VC by VS, volume clearance volume to the ratio of clearance volume to the swept volume is given as 3%, that is 0.03. Now the value of C can be written as C is equal to 0.03. Number of revolution through which the compressor rotates is given as 1000 rpm. Volume, specific volume at 1 dash can be written as 0.1.75. You can read it by the refrigeration table. Also similarly, V2 dash, the value of V2 dash, specific volume at V2 dash is given as 0.0262 meter cube per kg. Now the first thing we need to calculate is the theoretical power. So firstly, draw this TS curve and the pH curve for the ease of the calculation, and also showing the all the points, temperature points, for ease of the calculation. Now what we don't know is the temperature at the point 2. Firstly, we need to locate this temperature, that what is the temperature at point 2. We know the temperature at 1 dash, we know the temperature at 1 because degree of superheating is given as 5 degrees centigrade, 5. So now we need to calculate the temperature at point 2. But what we know is that the process of compression is isentropic compression. So entropy value at point 1 will obviously be equal to the entropy value at point 2. So we can read the value at point 1 dash and we can calculate the value at point 1. So entropy at 1 is equal to entropy at 2. So firstly we need to know this S1 value. So S1 can be given as S1 dash plus Cp ln T superheated divided by T saturated. You know the superheated value, temperature value, you know the saturated value. You know the S1 dash value from the data table. You can read for the Freon 12 at minus 26 degrees centigrade, you can read this value. Minus 28 degrees centigrade, you can read this value. So you will be finding out to be 0.7153 plus Cp 0.615, it is also given in the question, multiplied by ln of temperatures. Superheated temperature is given as 245 because the saturated temperature you will already know, that is 245 plus 5 degrees superheat, that is equal to 250. So we can calculate this value as 0.7277 kilojoule per kg Kelvin. Now you know the S1 value. So if you know the S1 value, now you obviously it will be equal to the S2 value. It will be equal to the S2 value. So we can calculate the value of T2 from here. So 0.7277, that is the value of S1, that is equal to S2, is equal to S2 dash, because you also know the value of S2 dash as well. From the TS curve you can see at 26 degrees centigrade temperature you can read the saturated vapor's entropy value plus CPG, that is the specific heat of vapor, ln T superheated divided by T saturated. Now you do not know this T superheated value, that is T2 value, but you can find it out from using. So you can have this T2 value as 319.7 Kelvin. Now we can also calculate the enthalpy value, because ultimately if we need to find out the COP or the theoretical power, you must have the enthalpy value. You know that H1 is equal to H1 dash plus CPG T superheated minus T saturated, as I already discussed before solving the numerical, that in the superheated region you can have this value. So H1 is equal to H1 dash plus CPG T superheated minus T saturated. This is your degree of superheat. This is degree of superheat. So we can directly write it as 5, or you can write it by 250 minus 245, it will be equal to 5. So value of H1 dash means the value of enthalpy of the saturated vapor at the exit of the evaporator can be given as 175.11. You can read it by the refrigeration table, plus 0.615, it is already given, multiplied by 5, you can reach this value. H1 is equal to 178.18 kilojoule per kg. Again, you know that H2 can be also be written as H2 is equal to H2 dash plus CPG T superheated minus T saturated, that is 198.11 plus 0.615 multiplied by 319.7 minus 299. You have already calculated this value, T2 value. Okay, 319.7 here we had calculated. So we can reach this value again, H2. Now the enthalpy of liquid refrigerant at point 3 how it can be calculated? H3 is equal to H3 dash minus Cp of liquid multiplied by T saturated minus T subcooled region, that is 4 degrees. Degree of subcooling is given as 4 degrees centigrade. So now you know the H3 dash value, because at 26 degrees centigrade temperature you can read the value of saturated liquid for Freon 12. So you can have this value 60.67 kilojoule per kg minus CPF value of the liquid is given as 0.963 multiplied by 4 degrees centigrade. Now you can reach this value. Now we know that the refrigeration effect per kg of refrigerant, how it can be calculated, that H1 minus H4, this is your exit point of the evaporator, minus H4, that is your H3 dash value, H3 value, not H3 dash. So we have this difference, 178.18 minus 64.52 equal to 113.66 kilojoule per kg. This is your refrigeration effect produced per kg of refrigerant. Also, what is given? Refrigeration capacity of the system is given. We know that refrigeration capacity is equal to mass flow rate of the refrigerant multiplied by the refrigeration effect produced. So it is your 12 tons of refrigeration. We can write it as 42 kilojoule per second or kilowatt. If I want to convert it into kilojoule per minute, we can write it as multiplied by 60. So how we can find out the m dot value? This is your refrigeration effect produced. We had already calculated in on the previous page, 113.66. So when I will equate 42 multiplied by 60 is equal to m dot into 113, now I can calculate this mass flow rate of refrigerant to be 22.1117 kilojoule per kg per minute. Also we can find out the work done during compression process. The compression process was represented by point 2 and point 1. Point 2 was the exit of the compressor, while point 1 was the entry to the compressor. So work done to the compressor can be given as m dot into H2 minus H1, that is the difference of the enthalpies. 22.17 kg per minute is the refrigerant mass flow rate multiplied by 210.84 minus 178.18. We can you can read it by the refrigeration table. This is the enthalpy value at the exit to the compressor, and this is the enthalpy value at the entry to the compressor. We have already calculated these values. So this is 724 kilojoule per minute or 12.07 kilowatt or kilojoule per second. Now we have COP of the system. We know that the COP of the system can be given as refrigeration effect produced divided by the work input to the compressor, or it can also be written as refrigeration capacity to the power input. They will both be giving the same answer. So refrigeration, we will go by this one. Refrigeration effect is given as H1 minus H3 divided by H2 minus H1. You can read it by the TS and pH curve. So we have these values. We can it is calculated to be 3.48. Now volumetric efficiency of the compressor. As I already told you that the ratio, this clearance ratio was given as VC by VS was given as 3% or 0.03. Now apply the Charles law to calculate the specific volume at the entry and exit of the compressor. We have V proportional to T. So V1 by T1 is equal to V1 dash by T1 dash, or we can calculate the value of V1, or this is the specific volume at the entry to the compressor. This comes out to be 0.1505 meter cube per kg. Similarly, we can calculate the V2 value, the specific volume at the exit to the compressor. This comes out to be 0.028 meter cube per kg. Now we also know the formula which was given as specific volume, the volumetric efficiency can be given as 1 plus C minus C P2 by P1. Now we know from the Boyle's law that P and V are inversely proportional, so we can write it by P2 by P1 can be written as V1 by V2, and this comes out to be by putting the value C is 0.03 and V1 by V2, the ratio of V1 by V2, if it was put here, the volumetric efficiency was calculated to be 87%. Now the next point is to calculate bore and stroke length of the cylinder. We know that the volumetric efficiency was given as actual volume entering the compressor to the theoretical volume or the piston displacement. Now the theoretical volume or the piston displacement can be given as actual volume, that is mass flow rate of the refrigerant to the specific volume at the entry to the compressor, divided by volumetric efficiency. This comes out to be 3.84 meter cube per minute. Since the refrigerating machine has 6 cylinders and a single acting compressor, so theoretical volume per cylinder per minute. Here we are calculating the theoretical volume handled by a single cylinder per minute. So this comes out to be 3.84 divided by 6, that is 0.64 meter cube per minute. Also, we know that the piston displacement per minute can be given as pi by 4 d square L into N, where L is the stroke length, D is the bore diameter, and N is the speed in RPM. So by equating these two equations, we have pi by 4 d square into L. Now the ratio of L and D was given as 1.25, so we can put the value of L in terms of D multiplied by the rotation value, that is 1000 RPM. This comes out to be 982 d cube meter cube per minute. By equating these two values, 0.64 meter cube per minute and 982 d cube meter cube per minute, we can calculate the value of D. That comes out to be 86.7 mm, and the stroke length, since the ratio L by D was given as 1.25, so the stroke length can be calculated as 108.4 mm. So this was the basic numerical problem where I tried to cover most of the fundamentals of vapor compression refrigeration system, which included the presentation of the chart, presentation of the cycle on TS and PS chart, allocation of all the points in subcooled and superheated regions, calculation of work input to the compressor, calculation of power input to the compressor, COP of the cycle, specific volume of the refrigerant at the entry and the exit of the compressor, and the length of the bore, length of the stroke length as well as the bore diameter. Thank you.